Next thing we're going to look at is the definite integral. So a definite integral is written like this, where we have the integral symbol of f of x dx, but then we also have these a and b values here, which are called the limits. So we would read this as the integral from a to b of f of x dx. And the way that we're going to find this is using that limit definition we looked at in the previous video that we used to find the area of a region. And our delta x here is defined in the same way that it was before. So let's look at an example where we find a definite integral using this definition. So to start off with, we're going to find the integral from -2 to 1 of 2x dx. Okay, so our limit definition here says we're going to find the limit as n approaches infinity of the sum from I equals 1 to n f of c sub I delta x. Okay, now our delta x is going to be b minus a over n. So in this case, 1 minus a -2 over n, which is 3 over n. And our c sub I is that delta x value times I plus the lower limit, which is a -2. All right, so then this is going to turn into the limit as n approaches infinity of the sum from I equals 1 to n of, our function was 2x, so 2 times 3i over n minus 2 times our delta x, which was 3 over n. Okay, now I'm going to simplify this a little bit. So both the 2 and the 3 over n here, none of those have i's in them, so I'm just going to go ahead and pull those outside of my sum. I'm going to make that the limit as n approaches infinity of 6 over n times the sum from I equals 1 to n of 3i over n minus 2. All right, then because this is being subtracted, we can split this up into two different sums. So I'm going to turn this into 6 over n. Actually, I'm going to pull even more out of this. I'm going to pull the 3 over n out front of this one as well. So I'm going to make this 18 over n squared times the sum from I equals 1 to n of I, and then minus 6 over n times the sum from I equals 1 to n of 2. So I split this into two different pieces. All right, now we can use our special sums that we learned in an earlier video to evaluate these. 18 over n squared. Remember, the sum of I is always n times n plus 1 all over 2. And then the sum of a constant is just that constant times n. All right, so let's clean this up a little bit before we take our limit. So here, first of all, I can see an n on top and an n squared on bottom, so we can cancel one of those out. And then the 18 over 2, we can just reduce down to a 9. And then here, the n over n will cancel out. This is going to be the limit as n approaches infinity of 9n plus 9 over n minus 12. Or, if we split up that fraction, the limit as n approaches infinity of 9 plus 9 over n minus 12. All right, so then taking our limit, this would be 9 plus, this guy would go to 0 minus 12. So that whole thing would come out to a -3. All right, so we're saying here that in the way that this is defined, the integral from -1 or -2 to 1 of 2x dx is equal to -3. In the next video, we're going to look at a much quicker way of finding these definite integrals, but for now, we're using the limit process. Okay, so the next thing we can look at here, as I mentioned above, that limit definition, we used it previously to find the area of a region. So that means that definite integrals can also be used to find the area of a region. So if we have a function and we're looking at finding the area between that function and the x-axis on an interval a to b, then we can find that by looking at the integral from a to b of f of x dx. Okay, so let's go ahead and look at a couple examples of finding area. Now on these, instead of using the limit definition, we're going to sketch out a geometric region and then just use a formula to find our area. Okay, so we're going to be looking for, on this first one, the integral from 1 to 4 of 4 dx. Okay, and this is representing an area. So let's go ahead and start by just sketching this out. Okay, this is saying y equals 4 is our function here. And we're looking at this interval from 1 to 4. Okay, we're trying to find this area in here. Well, what we've created is simply a rectangle. So to find our area, we just multiply length times width. So 4 times 4, which is equal to 16. All right, let's do one more like this. So the integral from -2 to 2 of the square root of 4 minus x squared dx. So for this one, we have to remember, first of all, what type of equation we're looking at here. So if we have our function y is equal to the square root of 4 minus x squared, if we square both sides of this, that would give us y squared is equal to 4 minus x squared, or rearranging it, y squared plus x squared is equal to 4. So you may remember that this is the equation of a circle that has a radius of 2. Now, because it's only the positive square root and not the negative square root, that means that we're only looking at the upper half of the circle. So we're going to be looking for this area right in here. So the area of half of a circle with a radius of 2. All right, so our area then, we're looking for just half of the circle. Remember, area of a circle is pi r squared, so pi times 2 squared. So that would come out to 2 pi. All right, so there's a couple examples using geometry to evaluate definite integrals when they represent an area. All right, the next thing we're going to look at here is the additive property. So what this is saying is that if we want to evaluate an integral from a to b, then if we can find some point c that falls within that interval, then we can break our integral up into two pieces. One integral from a to c, and then a second integral from c to b. Now this is going to come in handy in particular on functions like an absolute value function. So let's go ahead and let's sketch this graph out real quick. Okay, so the absolute value function, of course, is a nice V shape. look something like that. We're only focusing on this interval from -1 to 1. So we're going to be looking for this area right in here. Now, the reason we care about this additive property is because we can split this up into two different triangles. So we can think of this as the integral from -1 to 1, or excuse me, the integral from -1 to 0 of the left half of this, which would be a -x dx, plus the integral from 0 to 1 of the right half of this, which would be x dx. And both of these are just triangles. So our area, so the first piece of this, the triangle, is just 1/2 base times height. And then the second one, same thing, 1/2 base times height. So we have 1/2 plus 1/2, which is equal to 1. All right, a couple more properties of definite integrals. All right, so just to sort of quickly walk you through these. If we have a constant inside of a definite integral, we can pull that constant out front. If we have the definite integral of a sum or difference, we can split it into the sum or difference of two different integrals. If our original limits go from a to b, and we flip those limits to go from b to a, so we switch the order of our limits, then our integral is the opposite sign. And then lastly, if our upper and lower limits are the same, then the integral is always equal to 0. Let's look at a couple quick examples using these. So our first one, we're given 3 different limits here. The integral from 1 to 3 of x squared dx is equal to 26 over 3. Integral from 1 to 3 of x dx is equal to 4. And the integral from 1 to 3 of dx is equal to 2. And we're going to use our properties above in order to evaluate this integral. So we can split this up, pull out any constants, and then plug in the pieces that we were given. All right, so we can rewrite this. First of all, I can pull that negative out front. So negative integral from 1 to 3 of x squared dx. Then I can pull the 4 out front. Integral from 1 to 3 of x dx. And then I can pull the -3 out front. Just have the integral of dx. So then we can simply plug in the pieces that we were given. So we have -26 over 3 plus 4 times 4 minus 3 times 2. And if we do the math there, that would come out to 4/3. All right, let's see a couple more examples using these properties. So let's say we have 3 integrals that are given. Integral from 1 to 7 of f of x is equal to 3. Integral from 1 to 7 of g of x is equal to 2. And the integral from 4 to 7 of f of x is equal to 1. So first, if we want to find the integral from 1 to 7 of f plus g, we can split this up as the integral from 1 to 7 of f of x plus the integral from 1 to 7 of g of x, and then just plug in what we were given. So 3 plus 2 is equal to 5. All right, our next one, we can use that additive property that we saw above. So if we want to find the integral from 1 to 4 of f of x dx, well, notice we're given from 1 to 7 and from 4 to 7. So if we take the difference of these two, then we can find 1 to 4. So we're going to look at the integral from 1 to 7 of f of x dx minus the integral from 4 to 7 of f of x dx. So that's going to give us 3 minus 1, which is equal to 2. All right, next, the integral from 1 to 1 of g of x dx. We'll notice our upper and lower limits are the same here, which always comes out to 0. All right, and then lastly, the integral from 7 to 1 of g of x dx. Originally, we were given the integral from 1 to 7 of g of x dx is equal to 2. And if we change the order of our limits, then we just change the sign. So this is the opposite of the integral from 1 to 7 of g of x dx. So this is just equal to a negative 2. All right, so that is it for the definite integrals, and that's it for this video.